right, guys, let's take a look at question, or page 486, the homework questions that we had last night. Any issues with page 486, number 1 to 11, please? Number 11? Okay. Any others besides number 11? 7? 7-11. 7-11. You know what's good about 7-11? Slurpees. You know what kind of Slurpees are really good? Pepsi, but not the dark, runny ones, the light, icy ones. I really like those. Really like those. Yeah, really like those. Anybody have a spare period 3? Really? So you got lunch and then period 3 spare. Really, that's lots of time to get to 7-11, isn't it? I like Pepsi Slurpees. 5? 5 of them? You buy 5 days a week. Get to 7-11, buy Slurpees 5 days a week. There you go. Any others? All right. Number 5. Give 2 examples other than those in the textbook of possible collinear collisions. So a number of people were asking me what that term means. I'm not sure if we mentioned it or not. In the end, it's not something that we're going to lose sleep over the term. You have to know about collinear collisions, but you don't need to know the term per se. A collinear collision is just a collision that's in one dimension. So if it's a head-on collision or it's a rear-end collision or something like that, a one-dimensional collision. Again, you have to know about those, but the term, you're not going to be asked about that term on an exam. So we want to give 2 examples of collinear collisions with identical masses. Include a sketch of each situation showing the velocity of each object immediately before and immediately after the collision. One might be, here's object number 1, let's say, that's at rest. And let's say object number 2 is moving. Okay? Object number 2 is moving with a certain momentum. Okay? It's got a certain momentum as given by that vector. Let's say that after the collision, let's say they bounce apart. Okay? If they bounce apart after the collision, then it's going to look something like this. Object number 2 is going to be moving to the right, as is object number 1 going to be moving to the right. The 2 of these vectors combined must equal this vector. Does that make sense? The total initial momentum has got to equal to the total final momentum. Therefore, the momentum vector of the one object in the first diagram has got to be equal in length to the combined momentum vectors in the second diagram. That's what they really mean by that question. Does that make sense? Let's do another example. What if object number 2 was going this way with a certain momentum, and object number 1 was, let's make it at rest again. Okay, let's say this time they stick together. Object number 1 and object number 2 go off as one object after the collision. What's the momentum vector going to look like there? There's going to be one momentum vector, and how long is it going to be compared to the vector that we had in the first diagram? Should be the same length, right? The total initial momentum is equal to the total final momentum. So in the first problem that we did here, we said that both of these vectors have to add up to give me this vector. In the second one that we did, this vector is going to be equal to this vector because in both cases there's only one object that's moving. Make sense? Anybody have another example that they just want to check? There's a million other examples and a million other scenarios we could have, right? It's a head-on collision where they bounce off of each other, or, you know, head-on collision where they stick together. There's a bunch of examples that we could do. But no, we're good? All right, next one we want to take a look at is number 7. 7 says a liftoff, a space shuttle has a mass of 2.04 times 10 to the 6 kilograms. The rocket engines expel 3.7 times 10 to the 3 kilograms of exhaust gas during the first second of liftoff. 3,700 kilograms of exhaust in the first second of liftoff. Given the rocket a velocity of 5.7 meters per second up. At what velocity is the exhaust gas leaving the rocket engines? And they're telling us to ignore any change in mass due to the fuel being consumed. The exhaust gas needed to counteract the force of gravity has already been accounted for. It should not be a part of this calculation. If we were to do this perfectly correctly, which we can't, by the way, then it would be a much more complicated question than we'll deal with it as. Why would it be more complicated? Because the reality is that 3,700 kilograms of exhaust doesn't go out this rocket at once. It goes out over a period of time, over a period of 1 second. So it's actually a calculus problem to determine what the final velocity of this thing would be, because we'd have to look at what happens over a period of time, over a period of 1 second. Does that make sense? We're going to assume that it all leaves at once, though. So all this exhaust gas goes out the back at once, 3,700 kilograms. And then this rocket goes forward, of course, or upwards, I should say. We know that we're going to call this one M1. We're going to call this one M2. Everything's at rest initially, right? So VI is going to be equal to 0 meters per second for both of the objects. After liftoff, we're going to say that the shuttle has a velocity of 5.7. We're going to call that V1F, and we're looking for V2F here. We're going to say PI is equal to PF because it is like an explosion. We're going to say the total initial momentum is 0. There's one object. It's the shuttle and the gas combined, but that one object has no velocity, so of course it's not going to have any momentum either. After the explosion takes place, there's going to be two objects, the exhaust and the shuttle, M1V1F plus M2V2F. The mass of the shuttle times the velocity of the shuttle, 5.7, plus the mass of the gas, which is 3.7 times 10 to the 3, times the velocity of the gas. What do we end up getting when we do the math on that one? Negative something, right? Because this goes over to the other side by subtracting. Anybody have that? Negative 3.1 times 10 to the 3 meters per second. Anybody else get that? Make sense? Get that? Good. All right, let's take a look at the last question, question number 11 now. It says a 220 kilogram bumper car, car A, is going north. I'm going to change that to car 1. I don't like A's and B's. I'm not sure, it's just a little thing I have. I'm going to call it 1 and 2 as opposed to A and B. Anyways, it's going north at 0.565. It's another car going south. I'm going to circle this whole north-south thing because I want to remember that one of them's got to be positive, one of them's got to be negative. Bumper B goes initially south here. We want to find the mass of bumper car B, and we want to determine if the collision is elastic or not. Let's write down some givens here. We're going to call this M1. We're going to call this V1I, the initial velocity of the first bumper car. This one is going to be V1F because it's the car rebounding, the same car rebounding at 0.482, and it's going to be negative. Bumper car B was initially traveling south at 0.447. We're going to call that V2I. And after the collision moved north at 0.395, so we're going to call that V2F. No, this is going to be, the first one is going to be V1I, V2I, isn't it? Not V2F. This is going to be V2I there. All right, let's copy that over and create some space here. Let's set this up as a conservation of momentum problem. Even though we have both final velocities, we're solving for something different than we usually solve for, but it's still a collision, and conservation of momentum still applies. So let's do that. Let's say PI is equal to PF. Let's say two objects before M1V1I plus M2V2I equals, they don't stick together, so let's say it's M1V1F plus M2V2F. What are we solving for here? Solving for M2, right? At least that's the first thing we're solving for is M2. Let's plug in our numbers here. First mass is 220 kilograms. V1I is 0.565. Plus M2 times V2I. V2I is south at 0.447, so we're going to make it negative 0.447. M1 is, once again, 220 kilograms times V1F is V1F. Where's V1F? 0.482. 0.482 meters per second, but it's to the south, so let's make that negative as well. Plus M2 times V2F, which is to the north, so it's positive 0.395. Now, it's a little bit ugly because we've got M2 in two different places here, right? M2 in two different places. This gives people trouble when we're solving a question like this. It doesn't appear very often, but I do remember a question on a unit exam that I've given in the past, and I can't remember if I've put that question on your exam or not. But I do remember a question where we've had to solve for something like this. Okay, it's not really that bad. First thing we've got to do is kind of simplify things. What's 220 times 0.565? Somebody find that really quick for us. What is it, 124.3? Okay, plus, actually, it would be subtract, right? Subtract 0.447 M2. What's 220 times negative 0.482? Negative 99.44. And then we're going to add to that 0.395 M2. Let's take this over to the other side to combine it with the term that doesn't have any m's with it. So 124.3, how are we going to take that negative 99.44 over to the other side? We're going to take it over by, it's what? No, it's not actually. We're going to take it over by doing what? No, it's a negative number on the right side. We're going to take it over by adding. So it's going to be somewhere around 224. 224.2 or something like that. 223.74. .220 times 0.482 is 106.04. Yes? Okay. So that number's wrong then. So what is 106.04? Thank you. So that number is going to be wrong as well. So it's going to be somewhere around 230 then, is it? 230.7. Okay, so far so good? We've combined the terms that don't have anything with them, an m with them or whatever with them. Now we've got to combine the terms that do have an m with them. Answer this question for me, please. What's 3 plus 4? 7. What's 3 apples plus 4 apples? 7 apples. What's 3x plus 4x? 7x. What's 3m plus 4m? 7m. What's 0.447m plus 0.395m? That's what we're really doing here, right? Is taking this over by adding. What's 0.395 plus 0.447? 0.842. So it's going to be 0.842 m. That's it. It's as simple as that. We're just adding the coefficients there. Now, of course, we've got to divide 230.7 divided by 0.842. What do we end up getting for the mass there? 274.8, which we're going to round to, I think it's 3 digits here. 273.99, okay. Which is going to round to 274 kilograms. Perfect timing. Does that make sense? Does that make sense how we combine those m terms? That's the real challenge that people had, I think. Now, the next part of the question asked whether it's elastic or inelastic. We haven't had time to do that, but that's exactly like your quiz, right? Calculate EKI, calculate EKF, see if they match up. Good? Have a good break, guys. Your homework over the break is simply your assignment, which is due on Tuesday, your lab, which is due on Monday. If you want to do that conservation momentum worksheet, I think it would be a good idea. We'll check over a couple of those questions on Monday when we get back, whether you do it or not, and then study for your test. Have a great break, everyone.